After our little foray into conductors and how they behave in electric fields, we actually have a lot of the knowledge that we need to describe what happens to dielectric materials in an electric field. We're going to follow the same process that we had before to cover a lot of the similar quantities, and through that wrap up our discussion on the interaction between materials and electric field. Let's start with a discussion on what happens before and after an electric field is applied in a dielectric material. In a dielectric material with no electric field present, we have atoms that have positive, negative charges, but in general, they cancel each other out and just sit there. When we apply an electric field, remember that in the case of conductors, if the electric field is running down in this direction, so we'll call this E applied in this direction here, in the case of conductors, you'll have a bunch of negative charges here and positive charges here. You'll have positive charge densities on either side of the applied electric field such that they cancel out and you'll have no electric field in the middle. In the case of dielectrics, the charges are actually bound to the atom, so they can't move all the way up to the edge. But what they can do is they can slightly separate a little bit. So you'll have a slightly negative side and a slightly positive side forming a dipole. So instead of instead of these individual atoms that have no charge in them, now when you apply an electric field, they'll kind of separate into these number of teeny tiny dipoles that are slightly negative on one side and slightly positive on on the other side. And what that gives you is an E dipole, right? So all these dipoles add up to have a little countering E field. So it's not quite as strong as what we have in a conductor that is able to completely cancel it, but because of this slight separation into a slightly negative and slightly positive half, you do have a dipole that cancels out the applied field inside the material. And so inside the material, the total field is going to be equal to the applied field, but then there is this little dipole field that cancels out the applied field. So the end result is that while conductors completely cancel out the electric field so that there's no electric field inside, in the case of dielectrics, you have a diminished electric field in there. And the level of diminishedness kind of depends on how much these charges can move about and how tethered they are. And the closer you are to a conductor, the more this cancellation occurs. And then when you go to a full conductor, they can move freely and it completely cancels. So taking these dipoles into account, we can rewrite this equation and say that the electric flux density is going to be equal to the applied field in a vacuum plus a polarization term. So this term is called the polarization, and it is the summation of all these individual dipole moments. Remember that in the case of a positive and a negative charge separated by this distance, we define this vector as a dipole moment. So we add up all the individual dipole moments per unit area, and assuming that all of these little dipoles are identical, you have some finite number of them per unit area, which we can then rewrite into the permittivity of a vacuum with some coefficient, which we'll call the susceptibility. So this is called the susceptibility. And the bottom line is that this polarization term is going to be proportional to the electric field. So the greater the electric field, the greater the polarization, the greater these dipoles are collectively. If we plug this into our polarization term, we can then rewrite that the electric flux density is going to be equal to epsilon naught E plus epsilon naught times the susceptibility times E, which we can factor out the epsilon, lump everything else together into yet another constant, and we come up with a relationship that the electric flux density can be written as the permittivity of a vacuum times E times a relative permittivity, where this relative permittivity is 1 plus chi E. So this is a unitless term, but you can basically see this as an adjustment to the permittivity of a vacuum. So if you look at it a different way, basically epsilon r, as you can see here, it's always greater or equal to 1. If it's equal to 1, that means it's the same as a vacuum. But if it's not a vacuum, if it's any kind of dielectric material, this overall term will be larger than what it is in a vacuum. And so you can intuitively see here that the effect of the dielectric with these dipoles is that compared to a vacuum, for the same electric field, you have a lower density of flux lines. So the relationship, the flux line mileage that you get out for a given electric field is diminished in a non-vacuum material. And that is because of these dipoles that counteract the applied field inside the material. Let's go back to our Beyonce-Adele analogy that we had before. This is where it breaks down a little bit compared to how things work in real life. Well, actually, having Beyonce and Adele in the same concert is already mind-blowing enough to not quite be the same as real life. But here, let's take it a step further. So in the case of, remember when I said that a conductor, it's basically like an open floor concert where people can run around and go wherever they wish. In this case, for the case of dielectrics, it basically just means that there's fixed seating. So all of these fans, they are tethered to the chair, and magically, each chair contains exactly one Beyonce fan and one Adele fan. So you have these chairs here. The fans are completely stuck to the chairs, and they're also paired up. And so once you have this Beyonce and Adele playing in the opposite sides of the field, instead of being able to rush all the way to the front of the stage, all they can do is lean a little bit towards the performer of their choice and try to listen a little bit closely. And similarly for these Adele fans, poor souls, all they can do, they're stuck to their chairs with their Beyonce fan, with their fellow Beyonce fan, and all they can do is just lean towards the star of their choice. So unlike, remember in the past, there's the star results in some concentration of fans all the way over here, which satisfies all the fandom cravings. So there's no fandom craving in the center. Everybody's satisfied, and there's nothing going on in the middle because everybody's on the surface. In the case of dielectrics, they're just leaning as close as they can, and that doesn't satisfy them completely. So there's still some remnant fan dissatisfaction in the middle, meaning that the electric field inside is not zero. So continuing in the conductor, remember we had our discussion of, in terms of space, what the potential looks like. In the case of a conductor, you would have the potential coming down as part of the electric field, and then it would be flat because there's no field inside, so the potential doesn't change, and then it would come down again. In this case, you would have some kind of a slope, and then in here it wouldn't be flat, but it would be a reduced slope because you have a lower electric field countered by all of these dipoles. And then once you're outside, it would proceed at the same slope as it was on the other side. So now this is not flat. So after all this discussion, the main take home that I want you to have is the general understanding that the dielectrics have their charges bound to their atoms, yet they can still create tiny dipoles in the presence of an electric field. And the net effect of these dipoles is it tries to counter the applied field as much as possible in the medium, but it isn't able to do so completely. So the net effect is that compared to a vacuum, for the same amount of electric field, you will end up having less electric flux density. And the difference is described by this relative permittivity, this unitless adjustment factor that tells you how much to lower the E to D ratio compared to a vacuum. And this relative permittivity can be related to the susceptibility, which is a function which is related to the total amount of the dipole moments that you have created due to these dielectrics. Now let's wrap up our discussion with a review of what happens to the boundary conditions for a dielectric. So I'm going to draw a similar picture just as a reminder, but we won't go into this in the same level of detail. So recall that if we have two mediums, medium 1 and medium 2, and in this case we're talking about a general formulation that doesn't necessarily say specifically whether this is a dielectric or a conductor. The main way we do the analysis is to break the electric field into two components, where we have the normal component, and then we also have the tangential component, this is E2. And recall that to calculate the relationship between the tangential component, we use the fact that if we take E dot dl around this closed loop, we end up with 0. So when we do that, what we end up finding is that n cross E1 minus E2, or another way of saying tangential component, is going to be equal to 0. In other words, the tangential component is going to be continuous. And then separately, when we were doing the analysis for the normal component, what we do is we use Gauss's law across these two surfaces, ds1 and ds2. When we apply Gauss's law, as we've drawn here, we're going to find that n dot d1 minus d2, or in other words, the normal component is going to be equal to rho s. Or in other words, we can say that the normal component of d1 minus the normal component of d2 is going to be equal to the surface charge density. In the case of conductors, we found that we did some simplification by saying that the electric field in the conductor, if the conductor is medium 2, is going to be equal to 0. So we plug 0 for E2 and 0 for D2, and we found that E1 is going to be equal to 0 on the surface of a conductor, and D1 is going to be equal to rho s. In the case of dielectrics, we use the fact that we don't have moving charges, right? So you can't really create a surface charge density there. And so for dielectrics, rho s is going to be equal to 0. And therefore, your boundary condition is that, I'll just change into blue, since we were using blue to describe the tangential component. You'll find that the d1 is equal to d2. Or in other words, epsilon 1 E1 is going to be equal to epsilon 2 E2, normal component. I may have misspoken and said tangential before. And remember that you also have epsilon naught on either side, but they can cancel out. And so what you see is, in the case of a dielectric, the tangential portion of the electric field is going to be the same from one side to the other. However, if epsilon 1 is not equal to epsilon 2, you're going to have a change in the normal component of the electric field. So then when you add up the two vectors, you'll see that E1 and E2 are going to be in slightly different directions, because again, the green arrow stays the same, but the blue arrow changes if epsilon 1 isn't equal to epsilon 2. And so the electric field ends up changing direction as we propagate from one medium to the other. And ultimately, that leads to phenomenon that we're familiar with, such as Snell's law, where the light bends as it crosses from medium 1 to medium 2. That directly relates to this fact, that the normal component electrical flux density is continuous, meaning that epsilon 1 E1 in the normal component is going to be equal to epsilon 2 E2 in the normal component. Let's wrap up by doing a final summary of conductors versus dielectrics. So the general formula for boundary conditions is that for the tangential component, we have n cross E1 minus E2 is going to be equal to 0. And the normal component, we have n dot d1 minus d2, because it's Gauss's law, is going to give you rho s. So that's the general case. And the main thing that changes is the simplification we use when we're talking about conductors and dielectrics, right? In the case of a conductor, we use the fact that the field inside the second medium is going to be equal to 0, right? So if we're assuming that medium 2 is a conductor, we find that E1 minus is going to be equal to E2 and is going to be equal to 0. So the tangential component is going to be equal to 0. And the electric flux density of the normal component is going to be equal to rho s. Moving on to dielectrics, our main assumption, we no longer say that E2 is equal to 0 because you can have electric fields going across from one side to the other. So what you then find is that the tangential field is going to be continuous. So E1 is going to be equal to E2. And separately, for this, in general, we can assume that rho s is not going to be equal to 0. So if you wanted to be perfectly ideal about it, you can see a situation where, say, in the dielectric surface somehow is able to magically cut through the center of the dipole. But in general, overall, there isn't going to be a surface charge density on the surface. So rho s is going to be equal to 0, meaning that the normal component of D1 is going to be equal to the normal component of D2, or in other words, epsilon naught E1 is going to be epsilon 1 E1 normal component is going to be equal to epsilon 2 E2 normal component. So using the same approach, we have this general relationship that tells you how to relate the tangential and normal component of the electric field, or the electric flux density as it might be, from one side of the boundary to another. And again, by making the appropriate simplifications for a conductor and dielectric, you can find out how, once you know the E field in one side of the region, you know how to propagate that into a new medium if you were stuck on a desert island and somebody told you to do that.